Right, welcome Abigail, Nicholas, Michael. I think most of you were kicked out, if not all of you, so welcome back. Right, hi Caitlin, I'm glad you're back. Okay, now what I want to do, it's still the CH 2.4 standard, the exam standard, and what we're looking at are the properties. And I thought what would be a good idea to keep in mind, now can you see this triangle on the screen? So you can just type, yep, great. Okay. In chemistry, to do well, particularly at excellence level, you need to discuss all three focuses. So one, or foci, the first bit is the macroscopic properties. So what we see, feel, touch. Those are, if you like, the facts in chemistry, okay? Gold is malleable, it's shiny, it's a solid, okay, at room temperature. So those are what we see, your observations. So you describe. Now at achieve level, you are supposed to be able to describe these things. Then the theory comes in when we try and say, okay, how can we explain what we see? So this is your microscopic. I call this a 3M model because I made it MMM, but it's actually submicroscopic. So these are the explanations based on the particles. So like we can't see atoms, okay, although we're getting quite close to it, but we can just from measurements and so on, we've got an idea of what atoms look like and ions and particles and bonding. So that's where all the theory comes in. And as we learn more, the theory can change. Okay, so that's your microscopic. And then your model is your the way we represent the theory and the observations. So this would be your symbols for the elements, your equations, your formulae, and your calculations, all that sort of thing. So you need to have all three to do well in chemistry. Okay, so as an example, gold is malleable. You can hammer it and it'll change its shape. So that's a macro property. The microscopic property is where we say, or the submicroscopics, we say, oh, gold is made of a whole lot of particles called atoms, and these atoms are very tightly packed together in layers in 3 dimensions, and if I hammer on a few layers, then the layers can move over each other because the bonding is non-directional and it won't break and fall apart. So I know we haven't discussed metallic bonding yet, but can you see what I mean by the theory? So we've got what we see, and this is how we explain it. Okay, and you need to have lots of specific detail. The more specific detail you've got in your explanation, the better. And then you represent it. Now, in this section, there's not many equations and formulae to write about. There would be some formulae, but you would certainly have it in your calculations later on when you do thermochemistry. So I've just got AU to represent gold and the fact that it's a solid. So I put S in brackets to show the state that it's a solid. So always keep these three things in mind. And if you do the CH 2.3 standard, which is a report on either catalytic converters or polymers, you must show these three aspects as well. So you must describe what it is and explain and show that you know your chemical language by using lots of equations and formulae and so on. Okay, just going back over what we did last week. Remember, you got your 3 types of bonding. Sorry, we're into triangles here. Your 3 focuses, and now it's your 3 types of bonding. So the ionic bond, the covalent bond, and the metallic bond. And so everything is on a continuum. You don't have only ionic and only covalent. You get this changeover. But you don't have to worry too much about these middle bits. You just have to really worry about the extreme ends. Yep, so Caitlin, I have put the video up on YouTube, and you've got the Adobe link if you couldn't get see the video. The YouTube, when I download my things, the sound quality goes really bad. So I sound as though I'm on the bottom of the sea somewhere. So if you find the sound annoying, don't watch it on YouTube, watch the other link. Okay, now you will need to know about electronegativity, and that, as I say, it's a property of an atom. It's not a property of a molecule or a group of molecules. So I can't say the electronegativity of ammonia or the electronegativity of oxygen gas, but you can say the electronegativity of the oxygen atom or the electronegativity of nitrogen. It's a property of an atom, and it's a measure of how strongly it attracts the bonding electrons. So that's why it's got to be an atom, because two atoms bond, and it's how strongly they fight over those bonding electrons. So the one with the most electronegative will attract them more strongly. And that's why it can't be the whole molecule. It's got to be the individual atoms in the molecule. Does that make sense, what electronegativity is? Okay, it's the atoms inside the molecule all fighting over those bonding electrons. Right, and just so you know this trend, as I say, in level 3 you're going to do this in much more detail, but the most electronegative elements are on the top right. Fluorine is the most electronegative. And last week, I don't know if you remember, I asked a trick question about which one is most electronegative, and it won't be helium because group 18 does not bond, so it can't attract bonding electrons because there aren't any bonding electrons. And the least electronegative is down here. Francine, it's pretty much cesium. Francine is, francium, I should say, francium. It's so radioactive, it doesn't last very long, so nobody's actually really measured its properties, but certainly cesium they have. Right, you are given a periodic table in the exams, use it. Okay, I'll be referring back to this later on when I explain some properties, but let's first look at the 4 different solids you have to discuss in this exam standard, and those are ionic solids, metallic, covalent network solids, and molecular solids. So we're looking first of all those macro properties. Now I did do ionic solids last week, so does anybody want to, before I put it up there, give a few properties of ionic solids? So as an example, would they have high melting points or low melting points? So Abigail is typing. And the rest of you can think, would it be high or would it be low, and why? Because that's where you're microscopic. Yep, high melting point, brittle. Good. Okay, so that's your macro, and the micro would be explaining that. Okay, so I've got that it's brittle, it's hard, it can't conduct electricity as a solid, but it can when you melt it. Usually they dissolve in water, it depends on the solubility, and it has a high melting point. What about metallic properties? Now I know we haven't really done this, but usually in year 9 and year 10 you go over properties of metals. What makes a metal a metal? There are 5 properties that all metals have to varying degrees. So Abigail and Declan are typing. And quite a few of you are typing. Okay, delocalized electrons. Now Liam, correct, but that is the theory part. So we're looking just at the overall properties, so what you can see. You can't see delocalized electrons. We use that idea to explain what we can see. So I'm just focusing on what we can see, but otherwise you're on the right track for the explanation. Conductivity, malleability, right? So they can conduct heat. Metals can conduct electricity. You can hammer them into shapes. That's why you can wear copper bracelets or copper earrings and so on, or gold rings and so on. You can hammer them into shape. They're ductile, so your aluminium wires on those big overhead wires, taking electricity from all the various power plants to your house, and inside your house will be copper. Okay, because they're conductors and they're shiny. So shiny or lustrous. You may in the exam get lustrous. It's the same word as shiny. It's just a more Lani word, posh word. Malleable just means it can be hammered into shape. Ductile means it can just be drawn into wires. The explanation is the same for both. It's just some metals are more easily hammered and some can be quite ductile. Like gold, for instance, is very easy to hammer into shape. And I don't know if you've seen that very thin gold leaf. You can make it very, very thin. And in your one thing when you did the structure of the atom, Rutherford used a very thin gold foil because you can hammer it so much. It's not very ductile though, because it's so heavy that when you try and draw it into thin wires, it tends to sag and change shape and so on. Right. But it's still ductile. It's not as good though as copper. Conductor of heat, conductor of electricity, and they tend to have high melting points, particularly the metals sort of in the middle of the periodic table, top. The ones down at the bottom, if you think of which is the only metal that's a liquid at room temperature. There's one metal, there are two elements in total that are liquids at room temperature. One is bromine, a non-metal, and one mercury. So the ones down at the bottom, lead, mercury, gold. As I said last time, they go more under quantum physics rather than the general chemistry rules. So the heavier an element gets, it actually starts becoming more and more gaseous. I mean, we still have solids, but the new ones they are trying to make, like element 120, they seem to have more gaseous properties because they don't quite act as metals anymore because they're just so big. Anyway, you won't have to know that. You just talk about the general metals, okay, the upper ones. And but yep, so those tend to be a lower melting point, but the other ones are all pretty high. Okay. Covalent network solids. This is a bit of a disparate group. They can have lots of different properties, but generally they are hard, generally, and I'll go about discussion. But the only one that they really have in common is that they have high melting points. That's really the only property they have in common. And as I say, your only two elements that really make covalent network solids are, does anybody want to have a guess? There are two elements. The ones with the highest valency, and that are fairly small, carbon and silicon. So with carbon you get things like diamond and graphite. Now diamond is very hard, graphite is soft. It's used as a lubricant, particularly in places where it has a very high temperature, because graphite has a high melting point, so it won't melt very easily, not like oil that'll decompose. So the only real point here in common is a high melting point, and then we have to explain that when we do that. And we'll look at diamond versus graphite later. Then the molecular solids, and they generally are soft. Think of oxygen gas, nitrogen gas. When you take it down to a solid, not that actually you see oxygen as a solid very easily. So let's take something a bit different. Sulfur. Sulfur is a solid, that's a non-metal, and it tends to be soft. Or if you, right, so Abigail, the long twisted chain polymers, if they are just long molecules by themselves, just twisted together but not bonded together, then they tend to come under the molecular solids, because they're just simply long molecules of thousands of atoms in each molecule. If they cross-linked, like in your car tires, that the cross-linking, so you got your long molecules, but then they're also covalently bonded in themselves between the molecules. That now changes it to the covalent network solid, and the melting points increases. As you know from your car tires, they don't melt, on a hot summer's day. Whereas, that your polythene melts very easily. The glad wrap or cling wrap you put over your food, that melts pretty easily. Right, so we've looked at ionic solids, but, sorry, one more thing before we go into the others. You do need to know the type of particles that make up that solid and the bonding. So now we've done the macro, now we're going into the micro or the submicroscopic. We're now trying to do the theory to explain it. So here's our model representation. So actually diagrams are also part of the model. So our ionic solid is made up of anions and cations, where each anion is surrounded by a cation and each cation is surrounded by an anion. Okay. Metals, we say, are metal atoms squashed so closely together that the valence shells overlap, and so their valence electrons are free to move. They're not stuck with one particular atom. They can be shared, so this is like a snapshot, so these electrons are in the process of moving around. So they may have come originally from that atom, but they're moving around, and then this atom gets electrons from somewhere else. So they delocalize electrons, they can move around, and we say the bonds are non-directional. They can keep on changing direction all the time, so over time you can think of the attraction as being in all directions. Covalent, the electrons are shared and are very localized in a particular position. So those electrons that are being shared are stuck between those two atoms, and they don't move from between those atoms. So that gives the properties of the covalent network solid. Graphite is different again, but you've still got those sharing of electrons between the two carbon atoms over there, all the dark bonds. We'll look at that later. Molecular, our representation of that, or our model of that, is we have individual molecules having weak forces of attraction between them. So notice we just use dotted lines to show that those attractions are quite weak compared to a solid line that we do in between the carbon atoms. Well, here we can't even show any lines because the bonds are not directional, so our model doesn't show lines. And here we're also showing attraction in all directions, but it's still quite localized between this anion and that cation. It's just they do it all around them. Okay, so that's our model. And what are our particles? In ionic solids we have cations and anions. What about metallic solids? What do you think we'd find in metals? What sort of particles? So Abigail is typing. And the rest of you can think about it. So also what I want you to think about is the type of particles and then also the bonding that's there. Right, the metal atoms and the delocalized electrons. Correct, Abigail. Now, as I say, there's always, at every chemistry conference I go to, there's always discussion, can we say metal atoms or can we say metal cations or metal ions? Because the metal, if you're sharing your valence electrons, you've sort of removed some electrons, but you haven't removed them completely like in a cation. So metal cation and metallic bonding is not a true cation like up here, but it's not a true atom as you would have in the covalent network. So as far as I know, both metal atoms or metal cations or metal ions will be accepted. But then you've got to say the delocalized electrons with it, because that's the other attraction. It's your core metal atoms is another way of saying it, being attracted to all these valence electrons that are going around them. Okay. Oh, sorry, I didn't say the ionic bonds is between there. So it's metal ions or metal atoms or core metal atoms and delocalized electrons. And what sort of bonding would you find in metallic solids? Metallic bonding. Okay, so these are pretty simple. Ionic solids have ionic bonds. Metallic solids have metallic bonds. Okay, here you just have to say cations and anions, not atoms. Okay, this one is the metal atoms, ions, and delocalized electrons. What about your covalent network solid? First of all, what sort of bonding would you find in covalent network solids? So for covalent bonding. So those three are, the type of bonding is really given in the name. So that should be quite simple. What type of particles do we think of is covalent network solids? Sorry, I didn't say that question very clearly. What type of particles do we find in the covalent network? Now, Abigail, that's correct, but be a bit more specific. What type of atoms? They are atoms, but non-metal atoms, correct? Because you don't really get the covalent network in metals, only in non-metals. Now, Caitlin, I will answer that question after we've done this. We're going to go into the metallic bonding, and I'll explain delocalized electrons, if you don't mind waiting a short bit. Okay, so we've got non-metal atoms and their covalent bonds. And then finally, molecular solids. What sort of particles would we find in molecular solids? So Declan is typing. Again, the clue is in the name. So if you were given a table like this, it should be quite easy to fill in. Where it could be more difficult is if I said, for instance, here SO2. Then you've got to work out, is that a network solid, or is covalent network, or is that a molecular solid? But as I say, as a clue, it tends to be carbon and silicon. That's here. So SO2 would fit under here, and Si for silicon, SiO2 would fit under the covalent network. You would also be given a property as well, like you'd say SiO2 has a high melting point and SO2 has a low melting point. Explain. So that will also hopefully give you an idea that SiO2 comes there and SO2 comes over here. So we've got molecules, and what attractive forces are between the molecules? So in molecules, I know we have covalent bonding, but we're looking at the attractive forces between the particles, and the particles are molecules. So what attractive forces? The van der Waals. So you can say van der Waals forces of attraction or intermolecular forces of attraction. All of those would be correct. I would avoid the word bond. It's not incorrect if I said intermolecular bonds, but I find students, when they answer, they tend to leave out words in the explanation. So it starts sounding as though you're talking about the covalent bonds within the atom, because you might say SO2 is a molecular solid and it's got weak bonds and so has a low melting point. So the immediate question is, what bonds are you talking about? The covalent ones within the SO2 molecule, or the intermolecular forces between the SO2 molecules? So just make sure you're always very clear, very specific. Okay, so intermolecular forces or van der Waals, both are fine. Okay, so this is a summary of what we did last time. That's our theory. Okay, where do we find it? Metals and non-metal When they combine, it's a transfer of electrons, so we get cations and anions, and they're very strong. And our properties, the macro, is they don't conduct electricity, and this is our reason why, based on this theory. So this is the macro, this is the micro explanation. So these ions are held in 3 dimensions, so all the charges are fixed in position because they've got an ion in front of them, behind them, to the left of them, to the right of them, and they're stuck. They can't move. And remember, electricity is movement of charged particles. The ions are charged, but they can't move because they're stuck in the 3D lattice structure. I find a lot of students leave out the words like 3D. Use that 3 dimensions. It shows that you've got lots of attractions or lots of ions surrounding it, not just 1 or 2. Okay, macro property, brittle. Micro, the explanation, the lattice. If you disturb it, like put a hammer on it, you can shift the layers, but then what happens, unlike metals, a cation will get close to an anion, there'll be repulsion now instead of attraction, and so it'll all fall apart. So instead of being held together, it's now going to do the opposite. Okay. High melting points, because you've got to break lots of very strong ionic bonds. And there are lots of ionic bonds because it's in a 3-dimensional lattice. So you've got to break the bond, ionic bond in front, behind, above, below, to the left, to the right. So you've got lots of bonds to break, and they're all very strong bonds. So it's got a high melting point. Okay. And then solubility will be another one that can be soluble because remember we spoke about dipole and the shapes and polarity. We can form an ion-dipole attraction between the ions and the water, and often, not in every case, but often there's enough energy released from those pretty strong attractions to overcome the ionic bonds, simply because there's so many ion-dipole attractions being formed and the attractive forces between water. So that's what we did last week. So we're going to do the same thing, and that was, I don't know if I showed it, just as a joke, if you've watched James Bond movies. Right, so now we want to go on to metallic. Now, you should know where the metals are, okay? And as I say, these down here have more of a softer or lower melting point, but pretty much all these up here, well, perhaps not those so much, but all these have got pretty high melting points. Okay, but we consider they all have metallic bonding. Okay, now macro properties. Remember we said all those, so I'm just listing them there, but I'm not going to go over it. This is our model, our description. So Caitlin, you were saying what are delocalized electrons? If you can see, here are our atoms, and I've shown the valence energy level, and I'm trying to show that these atoms are all so squashed together that the electrons in that outermost valence energy level can move from one atom to the other. It's like a continuum, you know, it's like a passageway. Abigail, can I come back to you on that actually? Because I haven't got the answer off the top of my head. I used to know it, but I want to make sure I've got the right answer. So you've got these valence shells overlapping, so the valence electrons, the electrons in the outermost energy level, can move from one to the other atom, and they can go anywhere. So delocalized, you know, if you say, oh, I'm going down to the local station, I'm going down to the local pub, I hope you're not, unless you're 18. But it means in that same area. So if you delocalized, you are not limited to a particular area. You can go anywhere. So these electrons can move anywhere. So Caitlin, have I now answered what delocalized is? It's those valence electrons that can just move wherever they like. So if it's here being attracted to that atom, and then it can move around and be here and be attracted to this atom, and then move around and be attracted to that atom, and this one is now getting another electron. So overall it's having attraction to valence electrons, but at any specific point those electrons have moved around. Okay, so I've said the electron cloud that doesn't belong to any one ion. Okay, so the ions are fixed in position, or the metal atoms, but the electrons, the valence delocalized electrons, can move. So what I've tried to show here is, here are my core electrons, core metal atoms close together, and here are my delocalized electrons, or my electrons that are on the valence shell. And this one over here is being attracted to that nucleus, it's being attracted to this nucleus, and it's being attracted to this one over here. And similarly, this one is being attracted to 3 different ones as well. So the attraction is non-directional, because as this one moves, the attraction sort of lengthens and gets another attraction over here. I'll try and show. Okay, so I've got that there. They're not attached to any particular one. So I've tried to show them moving, and so this one has weakened and that one has weakened as it has moved up and strengthened there, and it's going to start forming another one over there, another attraction to a metal atom that's up here. So they can move around and the attractions weaken and strengthen all along as they go. So, okay, Abigail, I see you typing, but so what I'm trying to show here, these are the core atoms in a solid, they're constantly vibrating, okay? And if I put in the delocalized electrons, try and imagine the core atoms vibrating, but valence electrons can move around where they like. So I was just trying to do that in a PowerPoint, and I hope you sort of got that idea. Yep, I'll get back to you because I want to make sure I've got the right reason for that. Okay, Abigail? Right, so let's have a quick test. True or false? So you just have to say T or F in your answer. The term delocalized electrons means that all the electrons in a metal atom are free to move. True or false? False. Okay, it is actually false because the trick is in that word all. Only the valence delocalized electrons can move. Okay, sorry Caitlin, I do tend to make a little bit of trick questions because I want people to think, so I do apologize to those people that fall into the trap, but hopefully it makes everybody think about wording. Okay, so it's not all the electrons, those inner electrons aren't free to move, but the valence electrons are. Metal atoms are packed very closely together. True, correct. Let me just put that, okay? The attraction between metal atoms and the delocalized electrons are very strong electrostatic attractions. True, correct, okay? And an element with an electron configuration of 287, this is where you fish out your periodic table to see what that element is, and I can do that here. Which of those elements are going to be 287? Actually, you can't see that. You can't actually see there. So I've got to drag it out a bit more. Does anybody want to have a guess? Which one is 287? So 2 is the top row, 8 is the second row, 7 goes to chlorine. Will chlorine be able to form metallic bonds? No, because it's a non-metal. Okay, so that wasn't a sort of a trick question, and I was going to put that down a bit. Okay, so the answer to that is false. Okay, right, so metallic bonds, this is our theory. It occurs between metal atoms, that's why chlorine can't do it. They're very strong electrostatic attractions, okay, between the metal atom or metal ion or core metal atom or core metal ion. All of those would be acceptable. And delocalized valence electrons. That attraction is non-directional, and the electrons, those valence electrons, are delocalized. So they're not stuck in a particular area or bond, they can move around. So to explain the properties, this is the macro. Okay, because the electrons are delocalized, they actually can emit a wide range of light and reflect a wide range of light, and that's why they're so shiny. Okay, ductile and malleable are the macro properties, and the explanation, the microbit, the layers of metal ions can move past each other without breaking the non-directional metallic bonds. Notice these sort of key words. Use those words non-directional. Okay, don't just say the metal atoms can slide past each other. That's too vague. You haven't given enough detail. You've got the right idea. Okay, so the picture in your head's all right, but you need to now describe that picture in your head in detail, so that you're, as I say, imagine the teacher as being really, really dumb, doesn't know a thing, and you've got to try and paint that picture in their head as well. So use a lot of words. And being science, you know, you use scientific words. Okay, macro property is conduct electricity. Okay, and the delocalized electrons is now our explanation. They can move from atom to atom, they can move freely, they're not tied to a particular atom, and that's why, what is electricity? Moving charge, and we've now got moving electrons which are charged, so that's why it can conduct. And high melting points, because the metallic bond is strong, so it needs a lot of energy to break it. And actually what I didn't include in here, and I should have, is what? There's a key word I should have included in here. Do I only have to break one metallic bond to melt my substance? No. So what's the key word that I have forgotten to put in? The 3 dimensions. Okay, so you can rote learn the 3 dimensions, but also with excellence try and explain, you understand that in 3 dimensions there are lots of bonds to break. So you need lots of energy to break all these strong bonds, metallic bonds. Okay, so use that word 3D as well. Right, covalent bonds. So this is our next one, and sorry, I know I'm going actually quite sort of quickly through here. Are you okay with ionic solids and metallic solids? So if I give you a macro property, you can explain it on the microscopic or the particle level. So one of you have said yes, which is great, Abigail. The rest of you, think about it. If you're not sure, or you know, you may be thinking in your head, yes, you can, and that's fine. But as I say, your wording is very key here. So practice writing out your explanations. Yep, and Caitlin, you will be explaining these in quite a few teacher marked assignments, because the more you practice your explanations, the better. And actually when you answer these in the booklets, activities, check that you've got all these keywords and all the detail all the time, because the more you practice, the more likely you're going to use them all in the exam and do well. Okay. Right, so the network solid is based on the theory of covalent bonds. So the particles are atoms, non-metal atoms, and they're attracted by covalent bonds. So what's our theory? This attraction is between non-metal atoms, very strong attraction, and it's again electrostatic, but instead of between a cation and an anion, or between a metal cation and its delocalized negative electrons, we've now got it between the positive nuclei of one atom and the shared electrons. So it's still a positive and a negative, that's why it's electrostatic, but it's between the nuclei and the shared electrons. So if I've got 2 atoms in a covalent bond, both nuclei are competing for those shared electrons. Okay, and it's a shared one. The ones that aren't being shared, we're not concerned about. And we are saying they are directional. Those electrons are held in a particular place. Okay, I mean, they can still sort of move around, but they're sort of fixed between those two atoms. And so they can't hop from these atoms all the way down the chain to atoms down there. They are localized between these two atoms only. Okay, which means that those electrons can't move from one end to the other because they're stuck between those two atoms. And they're sort of quite rigid in that position. Okay, so it does give rigidity to a structure. Okay, so properties, high melting points. So that's a macro property. Okay, graphite does, and I'm going to explain this now, is to say the only common factor for giant covalent network is the fact that it's got high melting points. The rest, it really depends on the structure. So when you've got polymers, they're different to diamond, which is different to graphite, and so on. So this is a key point, that they have high melting points because you've got strong covalent bonds, and you've still got a three-dimensional structure, unless it's a two-dimensional polymer, okay? But we're looking at three-dimensional polymers, like you find in your car tires, okay? So you've got the 3D lattice with the covalent bonds sort of all around, holding everything in position. So you've got to break lots of bonds, lots of strong bonds in all directions in order to melt a giant covalent network. So that's the common one to all of them. But now we've got the diamond and the graphite. Now they can give you other ones as well. So they can give you silicon dioxide, which is similar to diamond, okay? Silicon dioxide is the basis, I think, for your emerald and your ruby and so on. So it's also very hard and very rigid, but not quite as hard as diamond. As a matter of interest, is diamond, and this is a trick question, I think you know me by now, is diamond the hardest substance known? No, it isn't actually. It used to be the hardest substance known until some scientists picked up a meteorite and tried to cut it open with their diamond power tools, and it wouldn't work. And it turns out that graphite, under incredibly high temperatures and pressures, will form a different allotrope. Now, an allotrope is just simply different arrangements of an element structure. So diamond and graphite are both allotropes because the carbon atoms, they're both carbon atoms, but here they're arranged differently to there. And these carbon has got quite a few allotropes actually. Your nanotubes, for instance, is one of them. But your lonsdaleite is now this new form that you don't really find on Earth. It's because the pressures and the temperatures are just so high. And it's really graphite that's been heated so much that these bonds here have become covalent bonds as well, and that's the hardest structure. Anyway, you can look it up if you want to. I just thought it was an interesting point. We always think diamond is the hardest structure. It is still incredibly hard. Okay, and why is it so hard? You have to explain that the carbon forms, each carbon forms 4 covalent bonds, very rigidly in a tetrahedral shape. So every carbon atom is stuck in its position with 4 others keeping it there. So it's there's no room for flexibility, and so it makes it really, really hard. If it's flat like this, where it's only in 3, each carbon atom is only held in 3, you lose that 3-dimensional rigidity. Okay, so that's first of all why diamond is so hard. You have to explain that each carbon atom is tetrahedrally bonded to 4 others, and the covalent bonds hold it very rigidly in that position, giving it its hardness. Then the high melting point is something like that. We've got to break all these covalent bonds. What about diamond? Does it conduct electricity? No. And the reason being is that all the electrons are being shared in these covalent bonds. They cannot move from one end to the other because they localize between the two atoms that are sharing those electrons. Graphite, on the other hand, is done in layers. So the layers, each layer in themselves is hard, is rigid if you like, but the layers are connected only by these weak intermolecular forces. We'll look at it. I know time's fleeting, but those are weak structures, so the layers can slide over each other quite easily. You don't need much energy to distort or to break these dotted lines, which are representing the intermolecular forces. And so graphite is a good lubricant because the layers slide over each other. So if everything slides over each other easily in the plane of the layers. Metals, remember, can be hammered in any shape because there's no particular plane. Graphite, you've got layers in a particular plane. So if I tried and smashed it this way, would the layers slide over each other easily? So if I'm applying a force from the top, no, because I'm going against perpendicular, and the layers can't slide. But if I'm pushing from the side, then the layers can slide over each other. So graphite is not the same as a metal, just in case you were getting that idea in your head. Okay, you also notice that each carbon is bonded to how many other atoms? Is it 4, or is it less than that? Less. Now it's actually 3, and I know it looks as though that one's only bonded to 2 and this one's only bonded to 2, but that's because we've stopped the thing going. Okay, but each is bonded to 3. So what happens to the 4th electron? Because carbon has got a valency of 4, it's got 4 valence electrons. Where's the 4th one gone? So Declan is typing. It's delocalized, so it can actually move within the plane and it can move around. And because that 4th electron is delocalized, it can move from one end of graphite to the other, and so it can conduct electricity. Because electricity is moving charge, this delocalized electron is negatively charged and it can move. Okay. I sometimes, by the way, get a question asked, what happens at the end? Here carbon has only got 2 bonds. There carbon's only got 2 bonds, and we know carbon's got to have 4 bonds. What happens at the edge of a crystal structure? Does anybody know? Okay, what it normally is most commonly hydrogen, particularly diamonds. If it's formed deep in the earth, it tends to get hydrogen added on the end, so you're actually going to get 2 hydrogens attached to these to give it its tetrahedral shape. And that's what diamond, if you freshly mined it, the way the miners would get the diamonds out is it would be totally non-polar, and it would not be attracted to water, but it would be attracted to grease. So they would grease the things that they were pushing the ore along, and then the diamonds would get stuck in the grease and the rest of the ore would wash over it. Okay, because the silicon soils tend to be more polar. Okay, but if a diamond has been exposed to air for quite a while, sometimes those CH bonds in the end are replaced with some oxygens to form like an OH or something like that. And so diamonds become more wettable. It'll attract water more because you've now got an OH there. That's just, you won't have to know for the exam, but it's just like interesting, fresh diamonds aren't very wettable. You can put it into water and take it straight out again and it'll be dry. It'll be totally dry if you take a fresh diamond and put it in water and out. But an old diamond that's been exposed around would get some water on it. Okay, intermolecular forces. I'm being distracted. The types of intermolecular forces you need to know at level 2 is the van der Waals as a general topic. Next year at level 3, you're going to break the van der Waals down into different types. Okay, but you just need to know this van der Waals, and you'd also need to know hydrogen bonding, which is, if you like, an extreme version of van der Waals that we give it its own name. Okay, what will influence the size of these attractive forces, these van der Waals? So van der Waals, he was just a Dutch chemist, and that's where that name comes from, where he investigated attractions between molecules. So what will influence the size of attraction between the molecules? What will make some attract more strongly than others? So in other words, why does I2 have a higher melting point than Br2, which is a liquid? And why does it have a higher melting point than Cl2, which is a gas? Okay, so what's the difference between Cl2 going to Br2 going to I2? What is the difference? Does anybody want to have a guess? Nope. Okay, can you see? Okay, I'll just get this up very quickly. I don't know if you can see. I2 is bigger. Let me make it. Okay, I2 is bigger. It's down here. So it's got more mass. Okay, and it's got more electrons. So the more mass a molecule has, and the more electrons a molecule has, the stronger those forces of attraction can form. Okay, so that's the first bit over here. Oh, okay, I thought I'd done the other one first. So the mass of the molecule and the number of electrons. The size of the molecular dipole, because remember when we did polarity of molecules, the size of the molecular dipole is also going to affect it. So if I have, say, HCl or HF, if I make this a bit bigger, okay, it doesn't really show in here. So H going with Cl, that's got quite a high dipole. So HCl, although it's a gas, I mean it dissolves in water, but do you think its boiling point will be higher or lower than H2? So one is non-polar, H2 gas, the other one is polar, HCl. Which one will have the highest boiling point? Does anybody want to have a go? HCl, because it's polar, it's got a bigger molecular dipole. Right, so I think we'll just leave that there. And then the shape of the molecule can also influence things. If you can pack molecules together closely, then they're going to form lots of areas where they can attract each other. Because there's if I have something like two flat things, there's a big space that they can form attractions. But if I take the same molecules and if they're round, can you see that the area between those round ones is a lot smaller? So can it form as many attractions between them? I hope you get the idea. There'll be fewer attractions between, so if I have molecules of the same mass but a round shape compared to if they've got a flat shape, because there's it can be attracted there, it can be attracted in the middle and attracted at the end. There's lots of spaces for it to be attracted. So those will all affect the van der Waals forces of attraction. So I've tried to show you here, the bigger the molecular dipole, the stronger the attraction. Okay, and as an example, CCl4 is nonpolar, but it's got a high mass, and compared to CH4, which has only got a very small mass, can you see the difference in melting points or boiling points? Carbon tetrachloride has got a much higher boiling point because it's got a bigger mass. So you may, at level 2, it's not so important, but it's good to be able to realize this, that there are varying degrees of intermolecular forces depending on mass, the shape, and the number of electrons and the molecular dipole. Okay, now I think actually, the hydrogen bonding is the other one, and I think this will be my last slide because I don't have any more. So you find it in molecules where the hydrogen atom is bonded to a very oh, I realize you can't actually see over here. Sorry. The nitrogen, oxygen, and fluorine. Sorry about that. Remember that electronegativity I showed you right at the beginning, where it increased from left to right? So nitrogen, oxygen, and fluorine are considered very electronegative, with fluorine being the most. So if I have a hydrogen attached to that, like NH3 or H2O or HF, then I can form a hydrogen bond between those molecules. So here's H2O. Note that this OH and that OH is a covalent bond. The same thing here, a covalent bond and a covalent bond within the molecule. But between the molecule, this positive or slightly positive hydrogen is attracted to the lone pairs of electrons on the oxygen. So that is my hydrogen bond. If you find it difficult trying to explain in words, draw a diagram and just label this hydrogen bond. And you can say very electronegative oxygen. You know, you're welcome to draw a label diagram. Use a model to explain if you're finding it difficult to explain in words. So you must make sure that you state that the hydrogen bond is formed between the H of one molecule and the oxygen of the other. So read your sentences and make sure, is the teacher going to see that, or does it sound as though you've said it's in the same molecule? Okay, and as I say, it's normally the strongest of the different intermolecular forces. And solubility, because we've got these strong hydrogen bonds, anything that has a nitrogen, oxygen, fluorine in it tends to be able to dissolve in water. And I think we'll leave it at there because it is an hour. Any questions? You all okay? Right, so I'll put this one up. Now I did hope to get the last solid done today as well. Yep, okay, Abigail, I will start with that in the next lesson, okay? Because I want to make sure I give you the right answer. So I will definitely come up with that.